Hi, everyone, and welcome to this episode of Crowded Beaker Solves. Today, we're starting a new series on gases and the gas problems that you're likely to encounter in a chemistry course. As a chemistry student, it won't take long before you start studying gases and what we call the gas laws. And if you imagine a gas, like a picture of a balloon or a container of a gas of some kind, there are a number of laws that sort of dictate how the gas is going to behave when things are done to it. I wanted to start, you'll probably get some sort of a chart like this during your class, and it has a list of what we call the gas laws, things like Boyle's law, Charles' law, Gay-Lussac's law. All of these are named after people, with the exception of the ideal gas law, which is like the one law that rules them all. And I'd like to start with the ideal gas law, but then we're going to move back to Boyle's law in this first episode. So, if you're thinking about a gas, like a balloon full of gas, there are four things you can measure directly about that gas. One, you can measure its pressure. That would be here. You could also measure the size, the volume of the gas sample. You could measure the temperature, and the temperature is going to need to be in kelvins. We'll talk about that later. And N, which is the number of moles. You could theoretically measure how many particles you have, or the mass of it, which you could change into moles. And those are the four basic things. The ideal gas law relates all four of those things, and I'll do one of those on a later episode. Um, but the other gas laws, these simpler ones, deal with describing what happens to, say, the pressure when the volume changes, or what happens to the volume if the temperature changes. And you'll see that most of these end up being pretty much like proportions. Like, for example, Charles' law says the volume is proportional to the temperature. And if the volume changes or the temperature changes, the volume will change proportionally to that. And so we're going to work our way through some of these gas laws. We're going to start here with Boyle's law. And Boyle's law is named after Robert Boyle, and he did a lot of experiments back in the 1600s, and he was the first to sort of put this together and say that the pressure of a gas is inversely proportional to its volume. So if you have a gas at a certain pressure and volume and one of those changes, the other one will change accordingly. So if the pressure goes up, the volume is going to have to go down. And if the pressure goes down, the volume is going to go up. And those two products are going to be equal to each other because we're assuming here that the number of moles and the temperature is constant. So we don't have to worry about those changing. So let's take a look at a problem similar to what you're likely to see. The problem here says a 3.4 liter sample of oxygen gas has a pressure of 741.1 millimeters of mercury. That's one of our pressure units. If it's compressed to a volume of 1.9 liters, what will the pressure be? So I encourage you when you get into gas law problems to just mark them up, make them messy, make it look like you're doing something. So this right here is a volume. So just label it as a volume if it helps. Over here, this unit that I'm giving, or this number, is a pressure. So I've got a P and a V. And I'm doing this because at some point you're going to have to decide which of these gas laws you're going to use to solve a problem. And it's helpful to label and see what you have. I have another volume, so we'll call that V2. Make these ones, these are the starting conditions. And the question asked me for the pressure. So I have two V's and two P's, which if I'm looking at a chart like this, it tells me I'm using Boyle's law here. So I encourage you then to, whenever you're doing gas law problems, actually write down the formula that you're going to use. I know you may have decided on it, but the person grading your work doesn't know that you've decided on it and wants to know which one you've decided on. So make sure to just write it. It only takes a second. And then you're going to want to start inputting your numbers. So initial pressure is 741.1 millimeters of mercury. And I also encourage you to put units on it because they do have units. And the initial volume is 3.4 liters. If it's compressed to a volume of 1.9, so I know this, but I don't know the P. So I'm going to put in just the P there for the thing I'm solving for, and the new volume is 1.9 liters. Now, before I do this, I'm going to kind of estimate and guess what my answer is going to be. Because my volume is going down, I anticipate the pressure to go up. You're compressing the gas and getting into a smaller space. So I'm going to use that as a way to check my answer. And if I go ahead and do this times 3.4 and then divide both sides by 1.9 to get P2 by itself, I get P2 equals 1326 millimeters of mercury. And the exact unit that you're using doesn't matter as long as you match what you're starting with in this case. So that would be my answer. So the volume went down, pressure went up. And that is what Boyle's law tells us. So now that we've got one under our belts, it's your turn to try a Boyle's law question. I'll read it and then we'll pause the video. A 6.0 sample of helium has a pressure of 1.2. If it expands to the point where its new pressure is 0.75, what will its new volume be? So take a moment, pause the video, grab your calculator, and see what answer you get. All right, good job for trying that. And if you were able to get an answer of 10.72 liters, then congratulations, good job on that one. We plug in the initial pressure, the initial volume is 6.7. The pressure has dropped. Note again that N and T are constant. And the new volume then went up to 10.72. And so that is a simple example of Boyle's law. So watch out for those problems where you only have pressures and volumes. Then your brain should say, I got to use Boyle's law, plug in your numbers with units, and show your work and get your answer. So there you have it, a simple Boyle's law problem. If you have a suggestion of a problem you'd like me to solve, whether it be gases or anything else, you can send that to me. In the meantime, happy solving and have a great day.